So Aldo is a professor of economics at the University of Minnesota, and he has quite diverse interests, including game theory, decision theory, experimental economics, and also neuroeconomics. Today he's going to be talking about some of his work on personality and social behavior.
Okay, thank you very much. So I will try to touch on three main themes. One is going to be the relationship between conscientiousness and strategic behavior. It is a comparison between conscientiousness and agreeableness, as we will see. The second is the theme that most fascinates me, which is the relationship between intelligence and strategic behavior. And the third, I don't know how much time we have for it, but I really think it is the most promising avenue, which is now we have to understand what are the biological processes that are underlying from the structural point of view and from the functional point of view the working of the personality traits. We have to begin to understand the biological part of these traits. Research here is very tentative, still is I think it's promise. And if there is a link with genetics, it's going to come. Research is common with many people, they can call them. It's a fascinating way of interacting with people. So let me start with the first one. So you can have two hypotheses on why people cooperate. One is that they have some preference over social outcomes, and which should be captured by agreeableness if you think of this in terms of the big pharma. And another one is some compliance with norms and rules, which should be captured by conscientiousness. These are two hypotheses, and so we can test which of the two is more important. To do this, we devised a game which is new, and it's very simple. First of all, it has one feature which is important to us, which is you have to provide some real effort, but it's not physical effort. You don't have to pump, but you have to add numbers, which is an effort, and it's probably worse than pumping. So you have to add digits. These are 2 digits, but 5 of them. And you have some time constraint to do it. Of course, you will be paid if the numbers are correct. There's a twist. You do it in 2 steps. You do a first sum of a series of numbers, so you get the first series of numbers. Then you do a second series of sums, and you get the second series of numbers. And then we will look, then in one instance we ask you to do the sum, in another we do the sum, but this last step is not really important. So the important part is that there is a 2-step procedure. First make sums, then you make sums, and then the correct answer comes from the combination of the two. The trick is going to be that in the control treatment you do both. In the real treatment, the second sum is going to be given to you by someone else. And you know this. So, this different treatment, you know that your sum is going to be correct only if someone else is doing the right sum. And you know that you are doing the same for the others. So, as the design, you have to add sums. You are in the control treatment, you do the sum. In the co-production treatment, you are part of a team, randomly matched. In some additional experiments that we have done, you get some signal of the ability of the person that you are going to be matched with, because of course you may want to know whether he is good at all with sums or not. But the key thing is this, that the second sum is not, the second addend in the sum is not the one you computed, but someone else computed for you. So the outcome now depends on how good the other person is. Since you know this, you will keep this into account also when you make the first sum, because you will take care of making the first sum correctly if you think that the other person is going to give you a correct correct answer rather than rubbish, otherwise. So the outcome now, it's clear, right? Now, whether you do the first one correct or not give us an idea how much you trust the other persons. How much effort you put in the second tells us how much you care about the outcome of the others. Because the care that you put in the second sum is completely irrelevant for you. It's relevant for the other guy. So that's what this bullet says. This is really a simultaneous trust game. If you know what the trust game is, this is a simultaneous trust game. So and there has both features of the trust game. That is the trust and the altruism. The trust in the first move, the altruism in the second. I think it's much nicer because it's balanced, there is no confusion for a second, okay? Balance. And you can make some nice variations. Okay, so the interpretation is clear, the number of correct answers that you give in the first, in the real treatment, is a measure of how much you trust the other people, how many questions you get correct in the second is how much you care about the other. Trust and altruism. And you can take those scores. Okay. Then you check what happens with the big five. I'm sure you have guesses. I'm sure they will turn out wrong. So the only two that matters are conscientious. This is for correct one, so it's a measure of trust. This is the 95 confidence interval. This is on the conscientiousness scale normalized between 0 and 1. This is the correct one. You will see the correct two in a second. Conscientiousness is positive. This is the control. This is the individual, the non-co-production. The interesting one, the treatment one is the shady one. Okay, so these are the one. This pain in the background is only, you should use it only, well, you can use it any way you want, but it's really virtual. Well, actually, it's interesting because look, I would have bet the other way. I would have bet the conscientiousness would be positively correlated with the performance even in the first and neuroticism. For the altruism, which is correct in the second, you get the same thing, almost the same thing for conscientiousness and for neuroticism. Agreeableness doesn't do anything.
And how do you measure the traits?
This is a very big 5 scale on one of the panels that we use, the BFAS. This is the young is one.
It's what?
It's your scale. The BFI is a subset of your items.
Yeah.
It's like 15 items of your 44 items.
Yeah, oh, is this the European? Is this the German study?
Yeah.
Okay,
Well,
so
it's using
three
those.
items. That's 3 items. Right?
So if you look at the regressions, you see the first column is correct one, the first and the second column is the correct one, with this with the interaction, this without, and this is second, this is correct too. So this is trust, this is the altruism. Not much effect on the first, but on the second. So it's really the one where you shouldn't have expertise. This is in the social interaction, how much you care about the others. So it seems that conscientiousness is heavily implied in the way in which you care about the others. Neuroticism is negative and the intellect is positive. So agreeableness. So here is the issue, right? Either agreeableness is really not measuring much. I mean, I've found agreeableness, sometimes it works, sometimes it doesn't. Of course, it depends on the scale of, we have a sample size which is much larger, then it starts doing something. It's really an ambiguous measure because it's really very much subject to the fact that you're sending a social signal of what you want other people to think that you are on something which is very important in your social interactions. So we added this, which gives us an extra control. This is a monetary effort experiment. So you can think of the monetary effort experiment as really the mirror image of the effort experiment, only you do it with money. So if you understood what the idea was behind the sums, it's almost the same, but it's a monetary transfer. So it works like this. You have an endowment of 10 units, and you have to decide how much you put in your own individual fund. So this is the investment that you do, for instance, when you do the sum, the first sum. And then you ask, you get another 10 experimental units, and you decide the quantity of X2 that is going to go into the investment fund of another person. And then there's going to be a technologist that is telling you how much you get out of these two inputs. They're anonymously randomly matched, and that's the technology. So you get the minimum of the two, you multiply it by 3, so there is a very strong return to scale, and then you pay your inputs, both to your investment fund and to the other investment fund. So this is clear, right? If you put a high X1, but the other person is not going to put in anything, you don't get anything. And of course, if you put X2, it's not helping you at all, because this X2 is going to be an investment fund of the other person. So it's not going to help you at all, but it's going to be subtractive. So as in the sum, but it is clear now, only one Nash equilibrium, which is contributing nothing and investing nothing, which is very inefficient. So now we can do two things. We can look at how personality works in this case, and how these quantities can be taken as measures of the trustful and altruistic attitude in the previous case.
Why not an exact mirror of the other game? Where,
I thought I was making an exact, okay?
pay and adding machine.
Oh, to remove the... Wait, okay, so this X1 goes into a machine. They will say, what, this is weird. I understand it would be, but what don't you think it would be weird? People will say, why do you put this
I mean, we're in a lab, a lot of strange stuff happens.
Okay. There's only one thing now that matters. So even conscientious doesn't matter, and it's only there. And this is, remember, is a combination, because it's how good you are. This is you're looking at the performance. It's how good you are in sum and how much effort you put. Look at how much can we use X1 and X2 to predict what you did in the provision of effort. And it's very nicely correlated. So a correct one, which we interpret as a measure of trust, is positively correlated with the amount X1 that you put, and correct 2 with the amount that you put in the amount that you put in the investment fund of the other person is correlated with the effort that you put in the sum that you provide to the other person. If you compare it with the two facets of trust and altruism, again you get that, even in this. So maybe an experimental measure derived by the experiment is better at predicting the behavior in this than the statement that you make about your experiment.
So, and the facets are from the NEO, but where are the facets from?
This is so we mimic we split the questions that we have into two, mimicking the standard division.
So it's based on the 3 questions, and you're using the question that asks about trustfulness.
So there's another thing that is coming now. Here is the skill in doing addition, of course, is positive, but once you control for batch, and now Um, oh, no, it's not here. So, okay, there's still in addition, of course, methods. So, summary, big five, the agreeableness is not associated with, we don't see any relation between the big five agreeableness and the behavior that you have in the effort provision. A measure that we derive from an experimental task is much better at doing that. The other result which we think is important is that cooperative behavior is heavily influenced by neuroticism, but most of all conscientiousness, so that there is an aspect of following norms and adjusting to rules in social behavior. And then there is the fact that intelligence is significantly positively affecting cooperative behavior, which takes me to the next topic, which is intelligence and strategic behavior. Okay, so that's my main slide here, if you want the point. But that I would like you to bring home is this. If you ask a random economist what he guesses the relation between higher intelligence and strategic behavior is, he will say that higher intelligence reduces behavioral biases. That's something that we saw in the talk this morning. Certainly reduces irrationality or incoherences or lack of transitivity in individual choices and reduces out of equilibrium behavior. That's the main idea. So this is my main point. This is very true when the game is strictly competitive. For instance, if a game is a zero-sum game. If the game is not with a single dash, if you are not there, I put it mildly here. So the key thing is when efficiency gains are possible. Efficiency gains are possible, the relation is much more complex. I really think it's completely wrong. So if you go and you study strategic behavior with the idea in mind that people are chess players, and the smarter you are, the better you are at playing chess, it's good for chess. It's not good for social behavior. In fact, maybe completely misleading. So the next set of experiments are trying to illustrate this point. So it's one thing is zero-sum games, one thing is not zero-sum. Big difference. So first, this came from an experiment around a long time ago, which had two games. One was the Heat 15 game, which is a math coefficient process game, and the trust game. The trust game is the standard trust game. There is a first mover that can transfer 0 and 5 to the second mover. The second mover gets that amount multiplied by 3, can decide how much it gives back. That amount is also multiplied by 3. There is going to be a huge difference between the behavior and this. This one we introduced and we studied it to death. Now we understand this Heat 15 game very well. Heat 15 is really a NIM game, is this game. Some people play it in school. You start here. You can move 1, 2, or 3. So you can put this here, or here, or here. Then the move goes to the opponent of the computer, depending on how the game is implemented. And it can also move 1, 2, or 3. That's it. The first one who gets to 15 moves. So it's a zero-sum game, but yes, it's a game, but since it's a zero-sum game, it's really a dynamic programming problem. There's an optimal solution, which is to move to 3, to 7, or to 11, if you can move there. And if you do, you win. If you don't, you lose. And to see this, I would like you to see this if you don't know it, because it's very good. That's the way in which people solve this game. Is that when you are here, and you have to move, you can go here, and then he will move here, and you lose. You can move here, and he will move, and you lose. You can move here, and he will move, and you lose. Now you understand that 11 is really the losing position. So Now you understand that 11 is like 15. You do it again, you do it again, and you solve it. I emphasize that this is the way in which people understand this game. This is not a game. So I think we have given up on this. This is a very nice, very effective. You have an IQ score in 3 minutes. I mean, it's really testing your ability to forward plan. That is really an IQ.
Is this related to the guessing game?
Excuse me?
Have you related this to the guessing game?
It's related. We haven't done the guessing game. You mean like beauty contest? Or? We haven't done yet a formal study of the two. You will see. We have done an experiment with Schindler that is related. We didn't do this with them. It's really so. It's very true. This is really testing your ability to. So this is using working memory because you have to keep in memory the output of the thought process that you have done plus recursive thinking. This and this. Plus here there must be a flash of light that tells you, this is the hallucination. Going back to yesterday I was having a discussion, why look at the brain? We looked at the brain when people do this, and it's very revealing because this wave going back from 11 to 7, at the beginning you see just a big cloud of dust. People are trying to think ahead and say, I move here, that moves here, that. You don't see it. Behaviorally or in magnetic resonance. But then you start seeing a very impressive regularity, which is, the first one you see is on the response time, because the response time starts picking up at this position in the early trials, because they are thinking, they're doing this. Then the response time here goes to 0, moves here, and then very quickly goes back. So there is a wave that you see in that. That wave you see in the brain. And it's very different from for people with high and low IQ. So in an experiment we ran, we had what we call fast learners and slow learners. And you can see this is in the first 10 periods, and this is in the last 10 periods. And let's focus on this, on the position. You are comparing the brain activation and position 11. And you see this big activation here of basal ganglia that are registered, oh, damn, I lost. And then you don't see it anymore. In fact, you see that it's slowly moving to 7 and then to 3, that way. And if you look at the slow learners, this picture moves on this side. Because they're getting there much later. So it gives us an indication of how people think about these things. It's an IQ. It's a very clear view. Some win, some lose. If you do the task game, then we found this, which really motivated a lot of my thinking about this, which I was surprised by. So, sorry, what does this picture say? This picture is quinterquartile IQ test, low IQ, high IQ, how much you transfer at the beginning. Game theory should say this, if you believe that. If you believe this intuition that smarter people are closer to the equilibrium, there is a single subgroup equilibrium here, so you should see the exactly opposite line.
Economics would not say that.
Excuse me?
Economics would not say that.
I said economics plus the fact that, plus this intuition that
You can argue about your own mind.
the economics handle, yes. So, the conditional on the fact, unless you think there is a very strong relationship.
No, the social preference is not clear what's up.
This is the content of our discussion. What is, I mean, let me, sorry, this is an empirical fact. I'm going to be taking about this. I mean, has many explanations.
No, it's just to clarify, these are the non-economics. That we have moved beyond assuming simple exact visualization functions. Which transforms the game into something less than
I just want to say, Here is a proof of. We now try to understand what is going on here. What is going on? The same for people that transfer in the second book. You have this paradox relation. This regularity, zero-sum game, non-zero-sum game, you find it in children, and I think it's interesting because so we did a study, age children between 3.5 and 9 years of age. And these are Minneapolis children, so Caucasian. The long study. So if you know it is the beauty contest, of course you can't tell the beauty contest to children, so you have to explain it with stickers. So you are sitting here, the experimenter is sitting there, you both put a number of stickers in a bag, you in yours, he in his. Then you look at how many stickers are in the bag. The one who has the lowest number wins that number. If there is a tie, nobody wins anything. So if the child puts 3 and the experimenter puts 4, the child gets 3. If the experimenter puts 2, the child gets nothing. And the experimenter gets 2. It's the beauty contest for children. Okay, so that's experiment.
What is it called, the beauty contest?
Beauty contest. The beauty contest is it's an idea as due to cancer has been implemented in games. And it's really it's a race to. So it has all the features of the beauty contest. There is only here there are 3 abbreviated, 2 of them are trivial, but we can obtain them by iterative elimination of weakly dominated strategy. There is only one thing that can happen. If you think about it, you should get to this conclusion. You can get to this conclusion by just thinking about what people are doing. So you think what I would do, then if you are patient enough to think what will they do, and then you put as an input what they will do into your thinking process, and you keep going back and forth to get to the conclusion that the only thing you can do is to put 0 or 1.
Assuming common knowledge of rationality.
I'm using here. Okay, I'm using theory here as a guidance in what to expect, and it has a striking similarity with what I find.
If you want to win the game, you should never go into a standard game. You should never say with an audience of with an opponent of your own skill. Sticker game was played for 10 rounds. Children knew this. It's a very interesting twist. So here I put the number of stickers by child in the first round. This is the first move. So after the first move, they play many times, so there is a lot of learning going on, they see what the other did, the analysis gets very complex. The first move is crystal clear. So it's, what do you do after you thought about it for a while? And this is the age in years. So that's the first thing you see, this is the lowest. So here, some people say, here nothing happens. Until age 6.5, 6, nothing happens. Then look at what happens here. Everybody, first move, goes to the unique equilibrium of if you do the regressions, of course, here is the age, which is very negative, very significant. But the age, remember, age between 3 and 6 is almost a measure of IQ. So you're really measuring the IQ. If you put in the information we had, an N backward score, I give you 3, it's 5, 6, and you have to see 6, 5, 3, and you have a bit stuff. So that's also significant. So IQ matters in the individual differences within the age, but also the age is. So you become a game theorist in the sense of game theory by the age of 6.5. There is a very interesting twist here. This is really not the context. If you think about it, it's repeated 10 times. So there is opportunity for cooperation if you think about it. Because you can, for instance, play, I put 4, you put 3, I put 3, and you put 4, I put 3, and you put 4. And then we get 3 each. Do we see that? So by the age 10 and 9, and we in the feedback that we get after, they begin to understand this. Yes. Remember, this is still in the first move. This is not something they learn. They understand that. So they are able to understand, oh, I should really put 1 or nothing, but if we all put 1 or nothing, we are not going anywhere. So maybe I'm better off putting, people put in 3. So you understand the scope of cooperation. So you see, even in this game correctly interpreted by children, that it looks like a zero-sum game. I can interpret what is going on. It looks like a zero-sum game, but it's really not a zero-sum game. We can cooperate if we want. Interpretation here are difficult. Maybe you are making a feint, I don't know. But there is room for cooperation. I'll skip this. Anche l'autodidà.
Hello, can I ask a quick question?
Yeah, I want to go.
Can you go back? So for age 0 to 6, what's the optimum response?
Oh, given these statistics?
Given the guys who play with it. That's my point.
I would say 2 and 2.
It's not 1.
Not 1, yes. But you agree that they don't go for this, right? Because
Now I take it seriously.
look at this. 3 stages of humanity: naive, selfish, cooperative.
That is impressive, yeah.
Naively rational, myopically rational.
Doesn't last long.
Excuse me?
Doesn't last long.
Oh, this one. Well, because I really think it looks like a zero-sum game, but it's really not a zero-sum game. Just an example, okay, this. When should I stop?
About 10 minutes.
So we really wanted to understand what is going on in intelligence and games. So we looked at the repeated game to get some intuition of what is going on. So we build on an understanding that we have now of a repeated game. So a repeated game is you play a game repeatedly. And there is, so the setup is double flash. You say you play a game repeatedly. This is the matrix of payoff. This is the prisoner dilemma. You can change this. The most important part is that with some probability the game ends. But with some probability the game does not complement, the game continues. So when delta is 0.75 with probability 3/4, the game continues. So if you look at the analysis standard, repeated game analysis, you would expect non-cooperation. Oh, this is what they get in the experiments, and is matching exactly what we see, what they see in the data. With the low discount, so this is the probability that the game continues, is fairly low, it's half, so it's the toss of the coin, the game stops. This is the fraction of cooperation, this is the number of repeated games that you have played. So very low cooperation when delta is a half, high cooperation when delta is 75. So that's the setup we use. We focus on this. So this is the matrix of payoff. Look at it for a moment. You would like to play this over and over again because it gives 48 to both. But if the other is playing this, then you have the temptation of deviating to 50. Once you do that, then there is the threat that you both end up in the only Nash equilibrium, which is 24. That's the spirit of the game. So we wanted to see what the interaction of people, of different IQ produces. So in the first day, we tested subjects on many individual characteristics, personality, IQ, risk aversion, a lot of stuff. Then we brought them back a week later. And this is the key thing. They played a repeated game. We put them in two different groups. One of high IQ and one of low IQ. So this is the distribution of the low IQ, this is the distribution of the high IQ. We split the middle, and we put the high IQ and low IQ. And then we look at the fraction of cooperation. So this is going to be the percentage, the number of times they choose cooperation over time. All rounds, so this is, we take an average over a certain number of periods and we plot how it goes. And there's a big divergence between the two groups. Do you have any guess who's who? Which is the smart one?
Oh, if your theory is
Yeah.
right.
So you're reverse engineering my answer. No, but this, okay, although this theory here, the theory, game theory, this is really sad. So this is the hierarchy, this is the lower. Why? So finally, I think we understand what is going on by looking at the data and running additional experiments. So checking this so first of all, there is not much difference in the first round between the high IQ and low IQ. Remember, this is a repeated game, so when they play the first stage, they are not in the position of the subjects in our previous experiment, in which you knew that that was the last one. You are going through every sequence of repeated games. But there is a huge difference in the, already in the first round, between low and high IQ in the percentage of cooperation. If you look at what this is, I think this explains what happens and what to do next, which is the most interesting statistics. This again is over time, and this is the probability that you cooperate with someone that cooperated with you the last time. So someone has cooperated with you, has been nice to you. What is the probability that you cooperate again in the next period? Red is low IQ, blue is high IQ. So that's the, looks like a small difference. But once you put it in the repeated game, it has this disastrous effect that you had seen in the beginning. Because it completely unbalanced and people defect. There is no substantial difference in behavior between when you are responding to someone that defected when you the last time. Everybody defects on defect. So this difference is large enough to make cumulative effects. And in fact, there is a huge difference also in the response time. This is the probability that someone, this is how much time it takes for a high IQ to decide whether to cooperate or defect. And it's clear that defection is a very problematic and difficult decision to take because they take about 1.5 seconds longer. Because it's the deviation from the mode that you now cooperate. For the low score, the response time is very simple. It makes a big difference on the amount of money you make. And it's important to understand that this is very sensitive to the payoffs. So you don't have that people with high IQ are cooperating no matter what. Because if we lower the delta to 0.5, then cooperation rate is even higher for the low IQ. The high IQ understand that there is no cooperation possible, so they go to defection.
Can I ask a question? So this is very interesting, but can you do some parallel experiments, or have you done, where you imagine changing the terms of the game by having some elements of uncertainty? So try to get some idea what the IQ is doing. Like, is it information processing?
I think we know.
You do? What is it?
I think this is true. This explains everything. Then so you will not see how the brain manifests. This is just actually I'll explain it recently. Prisoner dilemma. So people understand what the equilibrium is. And you see, in the prisoner dilemma, for instance, is this. In the battle of the sexes is alternating between the we ran this experiment. So there is a clear hypothesis coming, and we are testing, So this is the prisoner dilemma. The prisoner dilemma has this feature, and in the 2x2 games, this is a unique feature of the prisoner dilemma. You are here. There is a trade-off, a conflict between the short-run game. It didn't look like a prison. Okay. There is a conflict between the short-run game. If you know the other is cooperating, you gain 2 by deviating to 50. And the fact that you know that if you do this, then there is going to be a change in the continuation value because you might end up here. That's the basic, and this is what you see acting here. You are cooperating, and now these people make the evaluation of the comparison between current gain from deviation and future loss in continuation value. They are less clever in doing. So the implication of this, for instance, is that whenever you don't have this trade-off, then the difference should disappear between high IQ and low IQ. So for instance, in the battle of the sexes, this is the alternation. So the guess is that they will choose this equilibrium. Once we play this, once we play this. Everybody does that. But now here, there is no conflict. Because once you are here, and he is playing A, you don't want to deviate here. So there is no conflict between short run and long run. Stag hunt is the same. So they understand that this now, and only this is the stag hunt, it's almost like a prisoner dilemma. But now there is no conflict, because if he's playing stag, you want to play stag, you don't want to. Yeah.
This will have to be short. Actually, we check interrupting. It should be a very good discussion. We can enjoy over the paper images. So let me just say a few words which represent questions to be asked, which I think probe into the data that he presented a bit further. And if we start with one of the earliest graphs that was shown, this is conscientiousness versus score on, I think, the very first task that was put up. And what you see there is a fairly common phenomenon. The principal trend, of course, is described by this straight line picture, and I was pleased that there were these confidence limits that were put up there, which were relatively broad, but the main trend is clear. So that tells you what the predominant pattern is. On the other hand, if you look carefully at that, and not only that, and that's not the only one, you find there are people who have very low unconscientiousness that do pretty well on the task, and there are also some people who are high unconscientiousness that don't. And so this immediately raises the question, what is it about both the low conscientious people who do well on the task that still allows them to do that? Now, I don't know that this is a question answerable with the information that you collected, but I think response to that kind of question really begs for additional, let's say, mechanistic detail on what's doing that, about what may be a considerable subpopulation. Now, this phenomenon is not unique to the particular tasks that were shown, and I guess one of the messages that comes out here is always do repeated games, because I think you probably tend to see a bit more. But with regard to this question about people on the high end doing poorly and people on the low end doing well, I just wanted to mention one other context where this comes up and that I think is wildly understudied, and then I may have to go. There's, of course, very large literature on socioeconomic status related to an endless number of outcomes. I've gotten into that subject myself, largely with health outcomes, and a key thing that you see is there's a stratification system set up. It can be on the basis of income and on years of education,
And so the point is, there are strata there. And then the summary description is, people are showing you averages of outcome variables. They can be on biomarkers, they can be on scores on tests, they can be on the big five and what have you. But the emphasis is always that the people at the bottom of the hierarchy are doing poorly and people at the top tend to do well. And now we'd like to shift the discussion to getting rid of the inequality. On the other hand, what you often tend to see is that the further down in these hierarchies you go, the larger the variance in the variable that's being measured. And you find people who are at the bottom tier on economics, education, who do just as well as a lot of the people on the top. And the question is why? And in probing some of that in some of the health studies, what you find is the reasons are really quite different in terms of life experience, nature of challenges from those at the top. And that's not something to be surprised at, but it leads you to ask, why do this kind of investigation? Well, at least on the health end, one hopes that you can learn something from the people at the bottom of the hierarchy in terms of how they did well, and put it into an intervention which would allow a larger number of people also at the bottom to do better. And so I was rather struck by the, I guess, the presence of these low conscientiousness people doing well. I don't know if there's something that's known about them, or if that kind of question has been asked in your studies, because I'm sure the tasks that you're talking about here are not unique in terms of showing that kind of behavior. Now I'm going to have to get a card.
So conscientiousness enters into a very distinct way, right?
Okay,
How much you care about the task when it's involved in your own payoff, and how much you care about the task when it's involved in the other payoff. And I think the most surprising way the result was that conscientiousness enters into the performance of the task when you're doing it for someone else. That is not the way in which I was looking at conscientiousness. Then some people with low conscientiousness do very well because this is really not skill test, so there's going to be that factor that is compensated. So I would better if you look at individual outcomes and check how much the IQ of the low conscientiousness person is when it's doing well, that is experienced mostly. There was one comment that you made that I would like to pick up, but if you're leaving,
go ahead.
you always go repeat it again. There is an issue here. In experimental economics, we really focused for a long time on one-shot game, and we have to begin longer. There is, the tail is wagging the dog. We have, what is the relationship between your behavior and repeated game? What is your behavior in one shot? Most of them are the games we play in real life, right? More than, if you look at the number of interactions we have, I would say 90% of them are with people that you know you're going to interact with. So my working hypothesis is that our social behavior is influenced in learning from our repeated interactions, and then we export that to the one-shot game. This is an hypothesis sometimes is presented. I think we should start to test it, because the way in which personality is affecting your behavior even in one-shot interaction, maybe it's more affected by the experiences that you have in the repeated interactions. So there is one possible different way, is that the one-shot is really the purest form in which you can extract your social attitude. And the repeated game is artificial. I have the opposite. So,
No, I'm going to give you on the repeated game.
okay.
Okay, sorry, you have to. Okay.
Thank you.
We still have about 5 minutes if we want to.
Right. I have another methodological question. In testing and assessment, a fair amount is learned through table outs or retrospective discussion. That's particularly true as are complicated enough to have to do it consciously. They're not as helpful when you're doing just experiential thinking. Do you guys do much of that?
Yeah, well, I do. I do it this way. So I think the answer is yes, we do it, but we have now a more effective way of doing it. So we do it in this game. I did both methods. So let me illustrate this game. Do I have 5 minutes, Steve?
Yes, yeah, yes.
So this is the theory behind this game is called forward induction. And it goes like this. First, I can ask you to play this game, which is a battle of the sexes. You can either play this, which is good for me, and it's okay for you. Or you can play this, which is good for you and it's okay for me. Or we can disagree and we go to low pairings. Okay, so you can ask people to play this. Then we can ask them to play this with the additional, but now seemingly irrelevant information, that the first player had an option to move out, or to move in and play this game. We tell them, and now we study the second player. So we're not studying the player who chose to go out in the outline. Of course, we implemented the experiment, so there was the first move and the second. The idea of forward induction is the following. You are playing this game as the big player. You have to choose between that. But you know that the guy who has chosen to play now moves. And there we do eye tracking and we find out what categories of people. A category of people is very smart and understand that if a player could go out with 4 but did not, he's certainly not going to play doctor because he will get either 3 or 0, which is less than. To get to this conclusion, we have to do this. You have to look at these up. Look. So you see where I'm going. You can ask them, what did you think? So we went. What did you think? And you get unpleasant things like you see that in the trials in which you ask them what you did, you see that they're behaving more like a forward induction. All you can do is you put the eye tracking, the circle of this around the pairs. And then you can check what they look at and for how long. And then you correlate with that cue. So this is the outside option, this is the metrics game. And then we can check what they looked at. First you do cluster analysis, you find out there are 4 roughly group of people. There are people who are realistic, they only look at their own play. There is another class of people that look broad. There is another class of people that looks at the metrics, but never look at this. And then there's a smaller class of people, these, that look at both. So they go through the thinking process of the forward induction. And then you can do the correlation with this is the cognitive reflection test, this is the Raven advanced matrices. And look, this is beautiful. I mean, forward induction tells you that you are player B and you should do this. But you should do this, which are all payoffs that are not yours. You should look at O and the payoff A of the other guy. And in fact, they look at the people who are looking at the outside option A, correlated with CRT, very high and significant. Cognitive reflection task tells you in this game you should look at what the other person could have got. And you should look at the comparisons between the outside option and the metric. And you should look a lot at the comparison between the payoff of the other. These are not, you have nothing to do with this. This is not money. So going at this, again, in a well-structured situation, this is not even a zero-sum game, but clearly the cognitive activity now becomes very explanatory, very effective explanatory variable for deciding how people behave. And this is very close to this general intuition that I was saying of the people. I'm not saying that intuition is false. In this situation, hierarchy brings you closer to even sophisticated definements like normal. So I doubt that then when we look at repeated games, that the same principle must operate, that you are more sophisticated in your social interaction. Only the outcome is not going to be, oh, you are cooperating less, you are cooperating more. And we need to be much more sophisticated when we try to understand what organizes social behavior. It must be, the principle must be something that is, if you are smarter, you are more effective in processing all the information that is relevant for the strategic behavior that you are facing. In repeated game, it may lead you to this, I find this fascinating because it reminds me of many social situations as
That's very nice design there. It's a lot like in things that we do in assessment, where people are looking, if they're looking for the things that are meaningful, but are not necessarily obvious, you know they're thinking through the right schema.
Yeah. So we can answer
Yeah.
that. That was my
Yeah.
own answer.
Very
We
good.
do it, but we do it.
Yeah, don't even have to talk to people.
Yeah.